Today we are guested by Zaid Alyafeai, whose last name I got to butcher just now. Zaid is a third-year PhD student at KFU PM in Saudi Arabia. He works on Arabic NLP with a focus on how to teach language models how to learn morphology effectively. And today we'll be hearing about his work on fostering Arabic NLP through open source collaboration. And with that, Zaid, I will pass it over to you.
Thank you very much. Today I'm going to talk about a little bit of my work in Arabic NLP. This is a summary of the 2 years of work on open source in Arabic NLP that I have done with the different collaborators. So this is the outline of the presentation. First, I'll talk about Arabic NLP challenges using open source to democratize Arabic NLP. Then I'll talk about the transition from open source to research, and I'll give a little bit of overview of our work in other modalities that are related to NLP. So Arabic language is written right to left, and it contains many letters that are difficult to pronounce by foreigners, like these letters: Ba, Kha, Ha, Ghain, Wad. Arabic language contains special characters called diacritics that help readers pronounce words correctly. So here is an example of these diacritics that have been at the top of different characters, and they help in pronouncing short vowels. Compared to English, the Arabic language words letters, the letters are mostly connected. So we usually connect characters in different words. Some characters might not be connected, but a lot of characters are. In addition to modern standard Arabic, which is the most used in news and formal articles, so forth, there are different dialects in different regions around the MENA region, which is Middle East and North Africa. There are a lot of linguistics that are related to Arabic that might be a little bit challenging. So Arabic is a highly inflected language with a pitch morphology. Basically, there are mainly two types of morphology, which are derivational and inflectional. Inflectional morphology is used to inflect gender, tense, etc., from a given stem. For example, we have the word dhahaba in Arabic, which means go, could have the present tense yadhab, plural inflection yadhabun, and also feminine inflection dhahabat. In terms of derivational morphology, on the other hand, it causes changes to the meaning of a word or part of speech. For instance, given the stem kataba, which means write, could have the derivations katib, writer, kitaba, writing, maktaba, library. So now I'll talk a little bit about our work in open source, which is an initiative that started 2 years ago, which we called ArabML. It is really closely related to NLP, but we also support other machine learning techniques as well. So what were our goals behind this initiative? First, we would like to enrich the Arabic content by creating an open source projects or a set of open source projects. We want to open the community eyes on the significance of ML and NLP, create interactive applications that allow novice Arabs to learn more about machine learning and appreciate its advances. Also, we'd like to support research as well by providing developers and researchers with model prototypes, reproducible results, and open source datasets. And also, we would like to enrich Arabic NLP research and collaboration. So a lot of the tools that we do were the result of collaborating with different developers and researchers. So the NLP pipeline that we want to tackle is the following. We want to provide datasets through hosting and scrubbing. We want to provide processors, segmentations, and cleaning. We want to provide also tokenizers. And also we want to provide deployable models through notebooks and also our website. So our basic approach is that we want to foster collaboration in Arabic in the Arabic NLP field. So our approach is an open source approach that moves to academic research, and it's closely related. There are like some of the tools that we created that I will talk about in the coming slides. So, okay. So the first tool that we do have is called Bayanat, which means data in Arabic. So a lot of the tools that we call are they have Arabic pronunciation. So this tool is a very simple tool. It allows people to investigate different Arabic datasets. For instance, we can show the most frequent words, characters, and so forth. We can sample random sentences, characters, etc. And also we can plot embeddings. Most of the tools we allow using really easily through Python programming. For instance, here, simple code for using it. This tool can be used before cleaning because you want to investigate the dataset that you have, and if it has some problems, you'd like to fix them. So the second tool is Tnkeeh, which means cleaning in Arabic. For this tool, we provide a set of functions like morphological segmentation, normalization, social media data cleaning, diacritics processing, and we allow direct support with Hugging Face. Here is an example of using the cleaner that we have. First, you call the dataset from Hugging Face, then you call the cleaner with the functions that you want. For instance, here, remove the diacritics, and you just call the cleaner. We also support raw text files and pandas and other stuff as well. But this example is using Hugging Face. Tkseem, which means splitting in Arabic, is a dataset that is used for tokenization. The main functionality is being able to use different tokenizers. So here we have 6 types of tokenizers. I'll explain them more later in the research that we have done, but it's easy to know the functionality of some of them, like character tokenizer, word tokenizer, sentence-based tokenizer. I'll talk about the list or the others in a later slide. So here's a simple example of using the library. Just call the tokenizer, then you train on a text file, and you'll be able to tokenize, encode, and decode. Okay, so this is one of our recent tools that we have worked on. It's called Nmatheg, which allows you to train or fine-tune on different datasets or fine-tune on multiple models as well. So we support different tasks like sentiment analysis, sequence labeling, and question answering. Currently, we support 10 datasets from Hugging Face. So here's an example of using the. So you just like list the datasets that you want using the name from Hugging Face, and also you use the regardless of what is this what task is this dataset about. For instance, the first is sentiment analysis. I think the first three are sentiment analysis. ARCD is question answering, and the last one is named entity recognition. And also you can support or you can list all the models that you want to fine tune. All the models are BERT-based, but they are trained using different techniques and different corpora. And after you finish training, you will have like a simple table. It's like the one that you find in papers, but we make this much easier because you just can copy the results from this table, which makes it really easy to benchmark your, for instance, if you have a new model that you have, as long as it's supported by Hugging Face, you can just add it here, and you'll say, for instance, in another row, this is our results, and we achieved maybe better results or whatever at the end. Yeah. So yeah, we also like support deployment. The basic idea is that we want to make the models easily accessible by different people, but we don't want to host the models like in a certain website. The idea is that we use TensorFlow.js, which is a library that allows running models directly in the browser. It's a little bit challenging because you want to use much smaller or like so-called distilled models in order to run them directly in the browser. The idea behind that is that it will be a little bit expensive to host models. So the basic idea is we allow the models to run on the client machine using TensorFlow.js. So this is a pipeline that we do have, is that we have a collab notebook. We have like some examples for pre-processing datasets. Then we train on either Keras or PyTorch or TensorFlow. Then we convert to TensorFlow.js. Then we make all the models, datasets, and collab notebooks available in our GitHub repository. Here are some examples of the datasets that we provided. Some of them are related to computer vision, like digits, letters. Some of them are related to NLP, like poems, classification, Arabic translation, product reviews, image captioning, Arabic Wikipedia. Some of the datasets we use already existing datasets, but we pre-process them and make them much easier to use by people who are entering the field. Here are some of the models that we provide that are easily accessible and can be run directly in the browser. Some of the models we trained ourselves, and others are from literature, like for example, Arabic characterization, translation, poem generation, embeddings, and so forth. I think we currently have 10 models, and we provide mostly the collab notebooks and the demo for using them. Here is a simple example of the website that we have. Like it's in Arabic, but the basic idea is that we provide for each one of them the code, the collab notebook, and an online version that can be tried directly in the browser. Here's a sample example that we have for image captioning. the image on the left says that there is a giraffe in a field, and the one on the right is wrongly predicted as a set of sheep in snow. So these basic examples we trained ourselves, and we made them available in the browser. So we have done a lot of work in terms of open source. Now the idea is that we want to like move from open source to research, and we want to provide some like proofs that our tools actually work and can be implemented or used by different researchers for papers. So here is an example of a paper that we have done. So the basic idea of this paper is that we want to train a big language model, but the problem is that it's a little bit difficult to run this model in the browser. So we used distillation. So first we train a language model that is closely related to the mobile BERT model. We distill the model, the knowledge from the teacher model to the student model through weight transfer and pre-training. And we fine-tune the model in different tasks like question answering, part of speech tagging, and sentiment analysis. On this table on the right, we show the results and we compare to the state of the art at that time, which is Arabert, and this is our teacher model. We show that our model achieves better results in most of the datasets that we provide. For some datasets that are related to like ARCD, which is question answering, it achieves worse results. This is because we use much smaller vocabulary size. I think this model has 64,000 vocabulary size, and this one has, remember correctly, 50,000. We call it IBERTA. On the other two columns, we provide two student models. First one has around 30 million. So the first teacher model has around 67 million parameters. The benchmark that we are comparing against Arabert contain, I think, 135 million parameters, and these ones are 30 million and 15 million parameters respectively. And we achieved somewhat close results to the state of the art, although like in some of the tasks like question answering, we achieve worse results, which shows that for like more complicated tasks, the results degrade for Arabic. So mostly you need much larger models. And also these models were trained on like half of the dataset that's used to train the benchmark, which shows that you can achieve good results by training on smaller models and smaller datasets as well. So I said that we trained a smaller model for Arabic through distillation. The model has 14.2 million parameters compared to 135 million parameters for the benchmark that we compare against. This model, we fine-tuned and deployed the model in the browser, and we show here an example, which is that air conditioning is very bad and gives like a negative sentiment for this one, which with 98% confidence. So this shows that we can actually train smaller models for Arabic, although it's a little bit difficult for complicated tasks. But for sentiment analysis, it gives decent results. Although that might be related to the availability of datasets. We have a lot of datasets for sentiment analysis, but for Arabic, although like recently, some multilingual datasets were published, like TYD, QA, and others, but at the time, we only had a smaller data set, which had around 2,000 question answer pairs, I think. So another research that we have done is that we want to see the effect, like how much effective the type of tokenizer that we use for a morphologically rich language like Arabic. So the basic idea is that we want to use our tools and the different tokenizers that we created, and we want to compare them and see if they matter in terms of different datasets that we use. We benchmark these tokenizers on Arabic text classification. So just to show the pipeline that we are following and how much we are using the datasets that we have, or the tools that we have in our pipeline. So first we use Bayanat to visualize the data, and then we use Tnkeeh for cleaning. Then we use Tkseem for the different tokenizers. And finally, we use Nmatheg for evaluating and benchmarking the different tokenizers on different datasets. So this shows clearly that we are using the datasets, the tools that we have directly from our open source repository. This is a simple example of using the different tokenizers on Arabics. The first one is word tokenizer, which is a simple tokenizer that uses white space. The black squares indicates unknown words. It might have been better to use unknown token, but it's a little bit difficult to mix English and Arabic when writing, because from left to right and right to left, and mix things a little bit difficult to visualize. But this shows that for a fixed vocabulary size, here I think we trained on a 1 gigabyte dataset from Wikipedia on 10,000 vocabulary size, and here we use different tokenizers and compare them. Like the word tokenizer creates like 3 unknowns. The sentence-based tokenizer, which is directly ported from sentence-based directory, does not create any unknowns, but it creates a lot of segments or tokens indicated by the plus sign. We use like a simple stochastic tokenizer. The basic idea is that we think about stochastic tokenizer as a baseline, because we want to know if the type of the tokens that we generate actually matters. But when we use a stochastic tokenizer, we split tokens randomly without taking any frequency or meaningful morphemes into account. So this usually creates some random like tokenized words. This joint letter tokenizer makes use of the way that we write Arabic script. We know that in Arabic, not all of the characters in a certain word are connected directly. Like, for instance, here, an alif and ba, they are not written in a connected way. So we split based on that, and we use this as an individual tokenizer in our benchmark. The character tokenizer is a symbol tokenizer that splits every character. And finally, a morphological tokenizer, which splits morphemes. Basically, it splits prefixes and suffixes that have been, or they are connected to the word. Like, for instance, here, al, which means the in Arabic, and shabab, which means youth was split by the morphological tokenizer, although it's a little bit closer to the word tokenizer, which usually creates some unknown words. So now that we gave some examples on the different tokenizers that we have, we are trying to benchmark them against different datasets. So here we compare on two different datasets here. The first one is low resource, which means that it contains around 3,000 sentences. And the second one is high resource because it contains around 10,000 sentences. So we see that for the low resource datasets, the word tokenizer achieves the best results. The morphological tokenizer starts a little bit. It's the red one. I'm not sure if the labels are clear or not. The red tokenizer achieves words at the beginning, and as we increase the vocabulary size, here we use like 6 types of vocabulary size. We start from 500, 1,000, 5,000, 10K, 20K, and 30K. For sentence piece, it stops at 10,000 because I think the number of unique vocabulary is there in the dataset is around 10K. For highly resource datasets, we see that somewhat most of the tokenizers are close in terms of results. Actually, as we increase the vocabulary size, somewhat it's a little bit difficult to see which one or which tokenizer is better. Though the green one, the character tokenizer, achieves the worst results, which is reasonable because with the high morphology in Arabic, it's a little bit difficult to capture sentiment with character tokenizer. We also benchmark the different tokenizers in our pipeline on a poetry classification dataset, which is a 14-way classification task. So poetry in Arabic is interesting because the type of poetry or class, we call them in Arabic buhur, which means meters. So back in the days, like long time ago, the different the different poems had a different rhythm to them, and every poet would create a certain poem from a certain class of poems, right? So this highly depends on the characters. So we'll see that the character tokenizer actually achieves much better results compared to other tokenizers. Actually, like with the much smaller vocabulary size, like most of the tokenizers achieves better results, then the results decreases massively as we increase the vocabulary size, because it will have much chance of connecting morphemes together as compared to splitting characters individually, which will effectively create better results for the tokenizer for the task that we are tackling here. Finally, I'm going to talk a little bit about other things that we are working on that are closely related to NLP, but they are related to other modalities as well. So kalam, which means talking in Arabic, is like the first datasets that we add that are, or the first tools that we added that is not NLP, which is related to speech. So the basic idea is that we want to provide simple models that can be easily used by different people. So we basically provide two types of models. The first one is a speech classification model. So the basic idea is that we want to classify based on the dialect. For instance, in Arabic we have like a lot of dialects, and we want to classify into like Egyptian, North African, Gulf region, Levant region, and so forth. Also, we provide models for speech recognition, which converts like speech to text. And also we provide a model for text to speech, which converts like you give it a text and it will convert it direct to speech. One of our recent work is an Arabic calligraphy dataset, which was manually handled and annotated by the authors. Here is a simple example of using the of animating the dataset that we created. So basically, in this research, we collected a lot of Arabic calligraphy, and then we manually annotated this dataset using a tablet. And we collected around 2,500 handwritten calligraphy samples. Then we annotated the dataset on the stroke, character, and in the word level. And we are like interested in using this dataset for Arabic calligraphy generation. So it will be an like a very interesting application for this dataset. Okay, one of the, I think this is the last one, yeah. So the last one is that an interesting, like kind of interesting results that we worked on is an Arabic calligraphy image generation. We call it Rasm. So we trained a style GAN model on Arabic calligraphy. Unfortunately, like they are very closely related to aesthetically to Arabic calligraphy, but the sentences written are not readable. So they look really cool, but they are not readable, which says a lot about GAN's models. They cannot create readable content, but they will be able to generate some kind of the styles that are generated. We also create like a sample library to generate different samples from the trained models. So what are the future directions that we are looking into in the near future? So we are currently working effectively on the big science project. The main idea is that we want to enrich the data contents in the web by creating a big sheet for data sources, so people can access them easily using a simple API or a simple website. Also, we'd like to support more low resource tasks for Arabic. Most of the datasets that are available in the research that are related to Arabic are mostly sentiment analysis, and we want to support other datasets as well. Two things that we are currently working on is a poetry generation model using GPT-2, which we are training from scratch, and also an Arabic calligraphy recognition and generation model that creates readable calligraphy, at least. This is the hope that we are working on, although it's a little bit difficult because, as I said, we collected the largest set, which is 2,500, but I think it's not large enough for calligraphy generation, at least for the time being. We are thinking about increasing the size of the data set. In the last 2 years, we published 6 papers. Some of them are preprints and some of them like submitted, and like some of them are accepted in journals and conferences. Here are a list of the papers that we created. These papers are like a result of the open source collaboration that we created, and we are looking into like collaborating with more people in order to create open source projects for Arabic NLP as well. Yeah, that's it. Thank you for the listening, and I talked a lot about a lot of things that we worked on. I think I finished at time. So
yeah,
we
you're
have
perfectly on time.
questions.